Okay, everything is working, so we can start our lecture. At the last lecture we discussed the notion of symmetry in quantum mechanics, and the definition of symmetry was very simple. A symmetry is just a unitary transformation that lives invariant the Hamiltonian of the system. And today we'll consider some more examples of symmetries and then discuss the implications for the energy spectrum. And before continuing with examples, it is convenient to introduce a special class of, to distinguish a special class of symmetries that may be regarded as quantum mechanical counterparts of point canonical transformations in Hamiltonian mechanics. For lack of a better term, I will refer to them as geometric symmetries. Geometric symmetries. But this terminology is not conventional, so use it with some care. And okay, let us consider a quantum mechanical system whose states are described by multi-component wave functions. Say psi of q given by Coulomb vector psi1 of q psi n of q. So we are working in some q representation. For example, it may be a wave function describing a state of an electron or any other particle with non-zero spin. And then we say that an operator u acts geometrically in this q representation if it has the following form: S of q capital of q small, psi of q capital of q small, where S of q is some square n by n matrix, n by n matrix whose matrix elements depend on the coordinates q. And in order for this operator u to be invertible, we should require that this matrix S is non-degenerate. Determinant of S of q is different from 0. And so is the determinant of the Jacobi matrix associated with the coordinate change from q small to q capital. So let me write it this in this condition in this way: the absolute value of the determinant dqi dqj is greater than 0. Is greater than 0. Now let us check the unitarity condition when this operator u is unitary. It is easy to check because we have the definition of unitarity. We have to compute the norm squared of the transformed wave function psi. By definition, these are values given by the integral over q psi dagger of q is dagger s of q psi of q. Okay, here are by psi dagger I mean the Hermitian conjugate wave function, which is given now by a row composed of the complex conjugate numbers psi1, psi n. This is the definition of Hermitian conjugation. Okay, and now we can make the change of coordinates from q Q capital back to Q small. And after this change of coordinates, we can bring this integral into this form. dq, the Jacobian of the inverse coordinate transform, which is given by delta to the minus 1 power of q, psi dagger of q, s dagger q, s q, psi q. And if the operator u is unitary, this is equal to the norm squared of the original non-transformed state psi. And this norm is given by the integral over q space of psi of q, psi of q. Now we can put here the unit matrix and biomatrix, and then comparing these two integrals, I conclude that they coincide for arbitrary function psi, for an arbitrary psi, if and only if delta to the minus 1 as dagger as q is equal to the unit matrix. So this matrix in between psi dagger and psi should be actually multiplied by delta to the minus 1 should be equal to the unit matrix on the right. So this is a condition of unitarity, Okay, let me introduce, it is convenient to introduce operator, let me denote it T, which is given by the square root of delta. Delta is positive, so easily take square roots, and then multiply it by S. Then it is quite clear that this condition is equivalent to the unitarity of this new operator T. So T is a unit operator. T dagger T is unit matrix, provided that the matrix S satisfies this condition. Now, in terms of this matrix T, I can express my original unitary operator U in this way. U acts on psi of Q as square root of delta, unitary matrix T, psi Q of Q small. Of course, T is a function of Q, right? Notice that in particular case of scalar wave function, when we are dealing with one component wave function, this operator T, this matrix T, is just a phase factor, And in many practical cases of interest, this phase phi is just a constant, so we can ignore this phase factor without any consequence. This is just the inherent ambiguity in defining, in describing physical states by means of wave functions. So then the transformation U is completely determined by the coordinate change from Q small to Q capital, and in the configuration space of the system, and that is why we refer to these transformations as quantum mechanical counterparts of the point canonical transformations in Hamiltonian mechanics. The first three examples are that we considered at the previous lecture. I mean, permutations of identical fermions, special translations and rotations. They are all this kind. With delta of Q given by 1. This delta of Q equals 1. On the other hand, the evolution operator, which is a symmetry of any Hamiltonian or any system with some independent Hamiltonian, the evolution operator in coordinate representation gives us an example of non-geometric symmetry transformation. It should be emphasized that the property of being geometric depends on the representation we are working in. One and the same operator, symmetry operator, may be geometric in one representation and not geometric in the other. So the division of all symmetry operators on geometric and non-geometric is not absolute. And the same, by the way, is true for point canonical transformations. Okay, do you have any questions? No questions? Maybe in Russian? Okay. Now let me turn to the consideration of one parameter groups of geometric symmetries. One parameter groups of geometric symmetries. One parameter groups of geometric symmetries. As we know from the previous lecture, each such group, one parameter group of geometric symmetries, is given by a one parameter family of unitary operators of the form U of S is parameter, is given by the exponential function I S over H bar A, where A is some Hermitian operator. A is equal to A dagger. It is called the generator of the one parameter group. Is generator of the one parameter group. Whenever the operators U are symmetries of our Hamiltonian, the corresponding generator is an integral of motion, and vice versa. For each integral of motion observable which is conserved, we can define a one-parameter family of symmetries which form a one-parameter group. So there is a one-to-one correspondence between one-parameter families of symmetries and the integrals of motion, constants of motion. This is a quantum mechanical counterpart of the celebrated Noether's theorem. And at this point you may wonder what feature of the generator A makes the operators U geometric. In other words, which operators A define one-parameter families of geometric symmetries in the sense of the above definition. Okay, it is not hard to answer this question, but for simplicity, let us suppose that the coordinate transformations are unimodular, that is, the function delta, entering the formulas above, is equal to 1 for all s, And let us also suppose that the unitary matrix or matrices T of S they do not depend on the coordinates Q, so they are Q independent, just for simplicity. Then it follows from the definition of the operator U that the derivative of U with respect to the parameter S when evaluated at 0 gives us something proportional to the generator A. Specifically, we get I minus I over H bar A. So we can find the generator of a group of a one parameter group, just differentiating this family by the parameter and evaluating the result at 0. Evaluating the result at 0. It is quite clear that U of 0 is equal to 1. So S equals 0 corresponds to the identity transformation. And for geometric symmetries, this implies that the matrix T of 0 must be unit, and the coordinate change from Q small to Q capital must be identity map, that is Q I 0 of Q must be equal to Qi small. This is just the initial condition, for the family of unitary transformational. We may regard this as a definition of unit. Okay, now let us apply this formula to the case of geometric symmetries. For this end, I just act by this operator on the right, I over H bar, on some test wave function psi of Q. According to this equality, I can write this as the derivative of U at 0 acting on psi of Q. And now I can write this derivative in this way as a ds of for psi of Q, because psi doesn't depend on S, so this derivative hits the unitary operator U, and when evaluated at S equals 0, we get this expression. But now I can continue by substituting the result of action of the operator U on my test wave function psi. So I can write this ds T of S psi Q as Q small at S equals 0. Do you agree? Okay. And now I differentiate this expression by the Leibniz rule. So first time the derivative hits this matrix T, and then the wave function psi is a composite function, So I get the sum of two terms. The first one comes from T, and the second from the psi. So I get T prime at 0 times psi. Remember that at S equal to 0, Q of 0 is given by q small, so I can write this as psi of q small plus the second term r, which is given by q prime I 0q d dqi psi of q. Again, for s equals 0, the matrix T is just unit matrix, so I can omit it here. And then differentiated psi with respect to q and q with respect to s by chain rule, I get this expression. Now, since psi is an arbitrary function, psi is an arbitrary multi-component weight function, I can cancel both the spies with this quality by psi and get the following operator equality. I A hat is given by, let me denote this T prime by minus I theta capital, this matrix. This is just some n by n matrix. So then I get this theta plus I h bar q prime I 0q d dqi dqi. Well, this is the answer. This operator A, by definition, this is a generator of our one parameter family of geometric symmetries, one parameter group of geometric symmetries. And the following, we will use this formula repeatedly, so let me frame it in blue. Let me frame it in blue. Okay, can remove. Okay, thus we see that each one parameter group of geometric symmetries is generated by some first order differential operator with matrix coefficients. So the coefficients are some matrices, but it involves only 0 and first order derivatives in Q, if we are working in Q representation. The converse is also true. That is, every Hermitian first order differential operator that commutes with the Hamiltonian generates a one parameter group of geometric symmetries. And to define this group, we just need to exponentiate this first order matrix differential operator. By way of illustration, let us find the generators of special translations and rotations from examples 2 and 3 that we have considered at the previous lecture. And to begin with, consider translations along the first axis. So translations. As usual, I denote Cartesian coordinates in space by x. So the new coordinates x capital, x as x are given by x1 plus s, where s is either parameter of translation, and x2 of sx is given by x2 small and x3. So x2 and x3 remain intact. I translate only the first coordinate x1 by some value S. Well, now we just substitute this transformation law into the general formula for the generators A. At this particular example, I have no matrix factor theta. I have only this term related to the changes of coordinates, and identifying this Q capital with X capital, I can write immediately that the generator of translations is represented by the operator IH X prime I X D X I. So differentiating these expressions, these are X capital with respect to S, I get just 1, so this gives IH bar DD X1. DD_X1. But this is nothing else but the first component of the momentum operator, right? Hence we see that the translations of the first coordinate x1 are generated by the first component of the linear momentum. And in the same way, the translations along x2 and x3 are generated by the remaining two components p2 and p3. There is not much difference between these components. And all these generators, I mean p1, p2 and p3, are conserved quantities, are integrals of motions, whenever the space translations are symmetries of the Hamiltonian. Thus, we are led to conclude that the homogeneity of physical space, that is invariance under translations of the coordinate system, amounts to the conservation of the linear momentum of the particle, of the momentum of the particle. Okay, now consider rotations about the z axis, x3. Z axis. And from linear algebra, we know that the action of rotations on space vectors is described by the following equation. The new coordinates, or rotated coordinates, x capital, are given by the action of some orthogonal 3×3 matrix R on the radius vector x, where this orthogonal matrix R has the following form: cosine S, sine S, 0, minus sine S, cosine S, 0, 0, 0, 1, where S varies from 0 to pi. So here S is the angle of rotation. Angle of rotation about the z-axis, the vertical axis. It is clear that this matrix R is unimodular, so that delta is given by determinant R is equal to 1. And to find the generator of this family of rotations, we need to know the derivative of this matrix R with respect to the angle S. It is not hard to compute, and the result is given by this matrix R prime and 0. Through differentiating cosine, we get sine, and sine of 0 is 0. The derivative of sine is cosine. Cosine of 0 is 1, minus 1, 0, 0, 0, 0, 0, 0. So we get some anti-symmetric 3 by 3 matrix. Anti-symmetric 3 by 3 matrix. And substituting this matrix into the general formula for the generator, again we have no theta at the moment on this differential part. We find immediately that the corresponding generator A is given by the definition xi r prime ij d dxj. Okay, and substituting here the matrix elements 1, minus 1, and zeros, we get the following expression: x1 dd x2 minus x2 dd x1. And we see that this expression is nothing but the third component of the angular momentum operator. So this is familiar expression for the third component of the angular momentum operator. So we see that rotations about the z axis, x3, are generated by the z component of the angular momentum operator. In the same manner, one can see that the remaining two components, M1 and M2, generate rotations about the axis x1 and x2, respectively. So the general conclusion is that the conservation of the angular momentum, implies the invariance of the system under spatial rotation, that is, the isotropy of physical space. Is it clear? Do you have any questions? Please, don't hesitate to ask, maybe in Russian. Well, no questions. Let me check time. Okay. Now let me be more specific and consider a particle of spin 1/2. We know that in coordinate representation the states of such a particle may be described by two-component wave functions called spinors. Two-component wave functions called spinors. So psi1 of x. So x are Cartesian coordinates in space. Psi2 of x. Spinor. And the total angular momentum of a spinning particle, for example electron, is given now by the sum of its angular momentum m and its spin angular momentum s. So the total angular momentum is given by the sum. Given by the sum m plus s. Okay, let me put heads here, where the spin angular momentum operators are given just by the Pauli matrices. So sigma vector is just the set of three Pauli matrices, sigma 1, sigma 2, and sigma 3. Pauli matrices. Pauli matrices. As we know, for a free particle, both the vectors M and S are conserved separately because the corresponding operators M and S commute with a Hamiltonian of a free particle of spin 1/2. In a more general situation where the particle moves in the center of force potential, for example, Coulomb potential, and the spin orbital interaction is taken into account, only the total angular momentum and calligraphic conserves. Total angular momentum conserves. Let's consider the z component of the angular momentum, m3, which is just the sum of m3 plus h/2 sigma 3. And again, so we have some first order matrix first order differential operator, and comparing it with our general expression, we readily find that whenever this operator M3 is conserved, it generates a one-parameter family of symmetries, one parameter group of symmetries of the form U of S is given by the exponential function Is over H of M3. Now substituting here this sum and making use of the fact that these operators M3 and sigma 3 commute to each other, they act on different degrees of freedom, so we can factor this exponential function as Is over 2 sigma 3, Is over 2 M3 psi of x, and applying the first exponential function to the wave function psi, we get some t of s psi r to the minus 1 of s x. Because we know that the z components of the angular momentum generates rotation about the z axis, the vertical axis. And t of s is just this exponential factor. So here, matrix R is given by the expression above, and our t of s just exponential of the third Pauli matrix. But since the third Pauli matrix is diagonal in this representation, 1 minus 1, when we can easily exponentiate it. Just exponentiating each eigenvalue 1 and minus 1. So readily find that t of s is given actually by exponential is over 2 minus rs over 2, 0, 0. We get again a diagonal matrix. Now consider the full turn around the vertical axis, the z axis. What we get? Because r of 2 pi is given by r of 0 and is given by unit 3 by 3 matrix. So we just substitute instead of s 2 pi and we get the unit matrix. On the other hand, substituting here 2 pi, we get exponential I times pi, and this is a minus unit. So 2 of 2 pi is equal to minus 1. So we see that after the full turn, when the system comes back to the initial position, the corresponding two component wave function, spinor wave function, occur the minus sign. Minus sign. This doesn't cause any contradiction, since we do not attach any physical significance to the sign of wave function. This is just an inherent ambiguity in defining states by describing states by wave functions. The wave functions psi, plus psi and minus psi, they describe the same physical state. So this change of sign in a sense on physical. Well, any questions, please? No questions? Okay, then let's take a 5-minute break. Okay, let us resume our lecture. Before the break, we derived the transformation law, transformation property for the two-component wave function under rotations about the z-axis. These transformations are given by this formula, and these transformations are generated by the z-component of the angular momentum, total angular momentum, m3. And similar transformation formulas can be written down for the remaining two components of the total angular momentum, M1 and M2. More generally, we can consider the projection of the angular momentum operator, M, onto some vector S in space, in R3, some vector space projection. And this projection is given by the scalar product S with the vector M. If the corresponding operator, the corresponding projection is conserved, that is, commutes with the Hamiltonian, then it generates rotations about the vector S. I mean, well, clockwise rotation around the vector S. The corresponding symmetry transformation of the spinor wave function is given now by the formula U of S. S now is a vector, has three components. Space psi of x is given by exponential I over 2 S sigma psi r to the minus 1 S acting on x. So here R of the vector S is a matrix of the clockwise rotation about the vector S through the angle given by the length of the vector S. modulus of the vector S. So the angle is given by the modulus of the vector for unit. Okay. We take this expression as a transformation law, of the spinodal wave function, spinodal to component wave function, under the rotation of their coordinate system. When we transform coordinate system, we have to transform the corresponding wave function describing the state of particle, one half of the spinning particle in this coordinate frame. Now unifying space rotations with space translations, which we have considered above, we get a six parameter group of unitary transformations. Corresponding operators depend on S, rotation, parameters of rotations, and translations, A. So applying this operator to a spinodal wave function psi, we get some exponential factor as sigma times psi up to the minus y of S x minus a. Here a is a displacement vector corresponding to space translations. And by construction, this six parameter group, by construction, this set of operators define a six parameter group of geometric symmetries of particle of spin 1/2. Particle spin of 1/2. This is a six parameter Lie groups are six dimensional Lie group which is isomorphic to the semi-direct product of the rotation group SO3 rotation group and the translation group R3 semi-direct product. And finally, if we consider a wave function of a particle as a function of the space coordinates x and time, then we can extend the above group of geometric symmetries to the full group of non-relativistic space-time, four-dimensional non-relativistic space-time. This group is known as a Galilean group of symmetries in non-relativistic mechanics. Galilean group of symmetries of non-relativistic space-time. And by assumption, since we consider the wave function of a free particle moving in empty space without any force acting upon the particle, it must satisfy the Schrödinger equation. D psi dt is equal to minus h squared over 2m plus m psi. Okay, the Galilean group includes, besides our special translations and locations, also shifts in time, so we can translate time. And the corresponding transformation for translation in time, we simply prove that psi of x and t goes to psi of x t plus t naught. T plus t naught. So t naught is now the new reference point in the time axis. New reference point is time in the time axis, and it is quite easy to see that whenever psi is a solution to this Schrödinger equation, let me call it free Schrödinger equation, no potential, external potential, then this psi with shifted time argument is also a solution. So this transformation maps solution, any solution to the Schrödinger equation, again to a solution. As for transitions to another inertial reference system, moving with some relative velocity v, with some constant relative velocity v, one reference system, new reference system, with a velocity v are the corresponding transformations of wave function. Transformations are given by less obvious formulas, namely psi of x t goes to psi of x minus vt. This is quite clear, just from the classical mechanics. The transformation law for the radius vector in terms of new coordinate system, reference system t. But then we have some non-trivial phase factor. Scalar product v and x minus mv squared t over 2. So this phase factor depends both on x and t. And this phase factor is crucial. It is not hard to check that this new wave function will be solution to the Schrödinger equation, whenever psi is a solution. So again, this transformation maps solutions to the free Schrödinger equation to solutions, and the phase factor is crucial. Any questions, comments? Okay, if no questions, let me pass to the last issue of the present lecture. Now I would like to discuss a relationship between symmetries and the degeneracy of the energy spectrum. So let us write down the title of this part of the lecture. Symmetry and degeneracy of the energy spectrum. Symmetry and degeneracy of the energy spectrum. Okay, so consider some quantum mechanical system with a Hamiltonian H, and let E be its eigenvalue, some energy value from the spectrum of the Hamiltonian H. Generally, this eigenvalue E may be degenerate, meaning that there are several linear independent stationary states with the same energy E. Then the states span some subspace. Let me denote it HE. Subspace in the Hilbert space of all states of our system. This is eigen subspace corresponding or associated with the eigenvalue E. Now I claim that this subspace, eigen subspace HE, is invariant under the unitary transformations induced by the symmetry group of the Hamiltonian H. And to show the invariance of this subspace, we simply define the transformed state psi prime as U acting on psi, where operator U is a symmetry transformation. This from the symmetry group GH, and then deduce that if psi had the energy A, E, then so does the transformed state psi prime. And let us check. We just apply the Hamiltonian to the transformed state psi prime, and using definition of psi prime, we can write this as H U psi. Now we can commute H and U because U is the symmetry of the Hamiltonian. These operators commute to each other, so we can write U H psi. But psi is an eigenstates, eigenvector of our Hamiltonian H. So I can write this as E U psi, that is E psi prime. So I see that psi prime is the eigenvalue of the Hamiltonian, is the eigenvector of the Hamiltonian with energy E. So the fact that psi prime is from HE implies then transform vector psi prime is also from HE. So HE, the eigenspace, HE is invariant under the action of the symmetry group GH. In other words, we can say that subspace HE carries a unitary representation of the symmetry group GH. Carries a unitary representation of the symmetry group GH. If this symmetry group GH is big enough, this representation is most often irreducible. Anyway, being unitary, it decomposes into the direct sum of irreducible representations associated with invariant subspaces. So we can always decompose the eigenspace into the direct sum of invariant subspaces, which I will label by alpha, so that U maps each H alpha to H alpha. So each H alpha E is invariant subspace. That is the space of an irreducible representation of the symmetry group GH. And as we already know, only non-commutative groups may have irreducible representation of the dimension higher than 1, of complex dimension higher than 1. Therefore, if the symmetry group of a Hamiltonian is non-commutative, we may expect a degenerate energy spectrum, because the corresponding among these representations may be higher dimensional, 2-dimensional, 3-dimensional, etc. As a general rule, we take the following slogan. The larger the symmetry group of the Hamiltonian, the more degenerate the energy spectrum. The larger the symmetry group of the Hamiltonian, the more degenerate the energy spectrum. Degenerate the energy spectrum. In practice, if we deal with a full symmetry group and not just with a subgroup thereof, it is very unlikely that the representation associated with the eigenspace HE is reducible, like in this decomposition. It is as rare as it would be to find equal eigenvalues for an arbitrary matrix. Therefore, in practical situation, we may assume that the representation in each eigenspace HE is reducible, so that each eigenvalue E to each eigenvalue E they corresponds a definite irreducible representation in the eigenspace HE, reducible representation. So to each energy level, we associate some irreducible representation of the symmetry group of the Hamiltonian. In this situation, we speak about the so-called normal degeneracy. Normal degeneracy, meaning that the energy spectrum is degenerate, but each eigenspace carries an irreducible representation of the symmetry group. When two or more irreducible representations occur at the same energy, like in this decomposition with respect to alpha, then we speak about we use the term accidental degeneracy. Accidental degeneracy. An accidental degeneracy can be produced by the variation of some parameters in the Hamiltonian of the system, such as magnetic or electric strength, so that for some particular values of parameters, two normally degenerate energy levels cross each other. So we have to generate energy levels, and varying the parameters, we can under the variation of parameters, they move back and forth, and at some moment they may cross each other. Let me draw some picture. One degenerate energy level, another degenerate energy level with different values of energy, one, E2. But if our Hamiltonian depends on some parameters, like the strengths of external fields, electric or magnetic, these energy levels may can move back and forth, and for some particular values of the parameters, they may cross each other. Here we get two irreducible representations, with the same energy. Belonging to the same energy. If for a particular Hamiltonian, if for a theoretical Hamiltonian one finds systematic accidental degeneracy, sounds like an oxymoron, systematic accidental degeneracy, this most probably implies the existence of a larger group of symmetry. Let me denote it G prime, larger group of symmetries, which acts irreducibly in the eigenspace He. But this action becomes reducible when we reduce this group to the smaller subgroup GH. So this action is reducible with respect to the GH, but irreducible with respect to some bigger group GH prime. A famous example of such a kind is provided by the hydrogen atom, and we'll consider this example at the next lecture. Your questions, please? No questions. Okay. Symmetry considerations are also helpful in studying of splitting of degenerate energy levels due to various perturbations. As we know, in many physical problems, the Hamiltonian of the system is composed of two terms. Some dominant contribution and a small perturbation, So in many problems we can decompose the Hamiltonian of a quantum mechanical system. It is the sum of some operator H naught plus some small perturbation V. And it is often true that the operator H naught is much simpler than the total Hamiltonian H, in the sense that we can find exact solution to the corresponding stationary Schrödinger equation. I mean, H naught psi 0I is equal to I psi I naught, where I runs from 1 to some n. Let us suppose, for simplicity, that the eigenvalue E of the operator H naught has a finite multiplicity n, finitely degenerate. And as I have argued above, these eigenstates of the unperturbed Hamiltonian H naught, these eigenstates psi I, from a basis of an irreducible representation of the symmetry group in HRE, where the symmetry group GH0 acts irreducibly. Irreducible representation. Acts irreducibly. Now the account of small perturbation V, leads generally to splitting of degenerate energy levels E, and in particular the first order correction to E, to the energy E, corrections are defined by the so-called secular determinant equation. Secular determinant equation, which is given by determinant of n by n matrix composed of the matrix elements of their operator V, of the perturbation V. Is equal to 0. So calculated with determinant, we get some polynomial in the variable e to the 1. This algebraic equation from which these first order correction to the energy can be obtained. And if some roots of these algebraic equations are consigned, then the corresponding corrected eigenvalue E plus E1 remains degenerate. So in general, this algebraic equation may have some multiple roots, and if E1 is such a multiple root, that the corresponding eigenvalue is still degenerate. Let us now suppose that the symmetry of the perturbed Hamiltonian, that is full Hamiltonian H, is smaller or lower than the symmetry of the unperturbed Hamiltonian H naught. Then the symmetry of the Hamiltonian H naught. By this I mean that the symmetry group of the Hamiltonian H is a proper subgroup of the group GH naught. And in this situation we say that the perturbation V breaks some of the symmetries of the Hamiltonian H naught. So instead of group G H naught, we get only some subgroup GH, which is symmetry group of the total Hamiltonian. Okay, by definition, each eigenspace of the unperturbed Hamiltonian carries an irreducible representation of the symmetry group GH naught, this big group GH naught. And it is clear that it is also a representation of each subgroup GH inside this GH naught. It also a representation space for any subgroup of GH naught. But this representation with respect to the subgroup may well be reducible. May be reducible And this reducibility implies the splitting of energy level. Because, as I have told you, each different irreducible representations are labeled in general by different eigenvalues of the energy. They have different energies. So we are led to conclude that the number of different levels upon splitting the degenerate energy level due to the presence of perturbations, perturbation V is given, this number of different levels upon splitting is given by the number of irreducible representation, of the subgroup GH acting in the eigenspace HE, And this latter number, that is the number of reducible representation upon restriction to the subgroup, can be computed independently of the calculation of this determinant of these matrix elements. This can be done in purely group theoretical terms. And some examples of such group theoretic analysis will be considered at the next lecture. Okay, please ask your questions, if any. Well, no questions? Then let us stop here. The next lecture on Saturday.